Welcome to Biostatistics. The purpose of this first lecture is to make the material from the book more accessible to you. In some cases, the authors rely on mathematical formulas where it may be easier to understand in words. My goal for this lecture is to provide context for the chapter and relate the material as much as possible to what you have already learned from epidemiology. Much of Chapter 1 is a review for material you know. Specifically, I will draw on the links between Chapter 1 and the biostatistics you learned from epidemiology, namely prevalence, incidence rates, age adjustment, age standardization, and logistic transformation, which is in your SPSS output, even if you haven't done it yet. The section on logistic transformation will require you to look back on your output from the odds ratio results from last semester. I will walk you through the concepts in the worksheet, which was given as background reading last semester already. In summary, I will review incidence, prevalence, rates, odds ratios, and adjustment as an example of confounding. The worksheet is an assignment this week and is a further elaboration of the worksheet from epidemiology. This time it is an assignment because going through the steps will help you understand the relationship between what you have done already in the form of 2x2 tables and what we will do later this semester as logistic regression. The book starts with the concept of rates with the purpose of explaining that sometimes the term rate is used in epidemiology when in fact it is a proportion or prevalence. Food-specific attack rate is one example. It is not a rate because there is no time component. It is a proportion of those who experienced illness, in this case food poisoning, in relation to the number who are at risk. In other words, the number who ate that food. In this lecture and throughout the semester, I will put into words some of the concepts that are elaborated in the book as mathematical formulas. Rates, for example, can be written as a derivative, or can simply be understood as a change in the number of events over a given time. For example, miles per hour is a rate. This could be written in mathematical form, but can also be clearly understood from the context as speed. In epidemiology, all rates can be seen as a concept of speed. One needn't drive an hour to measure how fast one is going in terms of miles per hour. Likewise, in epidemiology, rate is often expressed in terms of person time as weeks, months, or years as a unit of speed to monitor when disease is occurring at a faster rate. An epidemic is identified when the speed at which a disease is occurring increases. People talk of a flu epidemic or the obesity epidemic. In that case, they are talking about new cases of the disease occurring more quickly or over a shorter time than previously occurred. This is monitored in measures of incidence and in terms of rates. You don't need to understand calculus to understand biostatistics. The formulas can be understood equally well in simple language, and that's what I'm going to show you on these next slides. The notations used are mathematical shorthand for indicating an instantaneous rate, derivatives, and for an average rate, an integral or area under the curve. To put the formula into words, a rate is new cases who experience the event in a specific time frame in relation to the population size at that time. The formulas showing death rates use the concept of the integral, which really just explains the process of averaging the rate over the whole time. This averaging process, which is reflected by the formula, explains why we use the mid-year population size as representing the population over the year. The mid-year population is used because over the whole year, the beginning and the end population is best summarized at the midpoint. The mid-year works based on the assumption that the deaths were distributed equally over the year. If all of the deaths occurred at the very end, then the end of the year would be a better summary. But that would not be a very realistic scenario. In Table 1-2 in the book, the authors give formulas to explain incidence and prevalence. They give these in the form of a formula, which I will repeat here in words to help clarify the concepts. The first two measures given are incidence proportion and incidence rate. The difference between these is that the first measure, the proportion, is just the number of the new cases divided by all those at risk. In other words, they didn't already have the disease at the start of the time period. The second measure is a rate, and therefore only takes into account a concept of person time. Person time over a year is the number who remain disease-free over the whole year, and assuming a steady state, each of the cases who develop the disease is assigned a half year. This applies the concept of the midpoint, assuming a steady state or an even distribution of the disease and those who became cases. The other two measures given in Table 1-2 are simple prevalences. These are prevalences at the beginning point prevalence at start 0, and at the end, point prevalence at the end. The difference between the start and end prevalence is that the prevalence at the end of the study includes all of the new cases who acquired the disease or the condition over the study time frame. So a point prevalence taken at a later time will always either be the same, assuming no new cases, or greater than, assuming new cases, the initial prevalence. However, this can only be true in a closed population where everyone stays in the study and survives. The exception is if the new cases migrate out of the population, are lost to follow-up, or don't survive the study period. If those conditions occur, the population is not closed, but an open population. Many of the mathematical assumptions rely on steady state and a closed population, when in reality incidence, in other words new cases, may not occur steadily over time, and most populations are open, meaning that you have loss to follow-up, migration, and death. Survival curves are important in longitudinal analysis where person time is measured. They represent the probability of survival over time. Hazard rates and hazard ratios reflect the opposite of survival and relate to the risk of a negative event occurring, indicated using the terminology of failure. The two concepts are directly related to each other, and this is meant to be reflected in Figure 1.3, showing that as survival goes down, hazard goes up. Thinking of this in terms of human survival, when charted to the age of 100, survival goes to 0. Few people live beyond 100. And hazard goes up exponentially after the age of 90. This is a visual representation of the concept of survival. In this figure, what you see is a study carried out in people, imagine they're at the age of 70 and measured over 20 years, with a hypothetical sample of 10 persons. In the first 2 years, 7 out of 10 survive. When at year 5, 6 out of 7 survive, with survival rates for each of the intervals where data was collected given at the bottom of the figure. So in the time between year 5 and 9, 5 out of the 6 people left survive. In the time period between 9 and 16 years, 4 out of the 5 people survive. And in the final time interview, all of the remaining 4 people survive between 16 and 20 years. At the end of the study, 4 of the 10 who started the study have survived. If survival were measured as a conditional probability, the answer would be the same. The total survival would be calculated as the number of deaths divided by those at risk. The hazard is exactly the opposite. That's the number who did not survive, so the number of deaths over the total initial sample. If we look at survival and hazard in terms of the person time, this example shows how person years would be analyzed if person time were known in the intervening time points at 2, 5, 9, 16, and 20 years. In each instance, everyone is attributed the person time for the interval they survived. The midpoint assumption doesn't hold up because the deaths are not evenly distributed or averaged over the 20-year time frame. 3 deaths occurred in the first 20 years, whereas no deaths occurred in the last 4 years. In the book, you also see a section on smoothing, and I just wanted to give a brief introduction to why, when, and how it's used. In statistical analysis, very often data doesn't fit a simple formula, but has to be smoothed to the nearest line or curvilinear function. In the book, this is shown graphically in figures 1-5, where the actual data is shown on the left side of the graphic, and then smooth data is shown on the right side. The smooth data allows for analysis that can be predicted using a formula. But why do we do this? In research, data is smoothed to fit a predictable pattern. For example, in my own work, I know that growth does not occur in smooth equal increments. It is used to create, for example, smooth growth charts that predict how children should grow using a mathematical formula. So smoothing is used to make use of real data on growth, which is not smooth, and assumes that changes occur in equal increments to flatten the results to fit the shape of a line or a curve that will help us predict a specific outcome. In epidemiology, you actually did some adjustment. The book describes adjusting mortality rates by age, and at the end of chapter 1 there's a section on age adjustment. We talked about this also in terms of age-adjusted obesity prevalences in previous lectures in epidemiology. The book describes additionally adjusting mortality rates by age to directly compare 2 populations. Although you won't be doing this process in this class, it is important to understand the literature on age adjustment. The book describes adjusting mortality rates by age. These are used to directly compare 2 populations. Just as in the example I gave for the age adjustment process for obesity prevalences, the process applies real age-specific rates, so mortality rates in the book, obesity rates given in the example from epidemiology, to a hypothetical age structure. So in the example from epidemiology, see that lecture on age adjustment for overweight and obesity prevalences in Europe, where the age structure of Europe was used as the hypothetical age population, where the actual real prevalences were applied to get comparable age-adjusted obesity rates. Another approach sometimes used is indirect standardization. While the explanation in the book is a little hard to follow, indirect standardization is simply where the age structure is kept the same, and it's the mortality rates from a standard population that are applied to the actual real existing age structure. So whereas direct standardization compares 2 populations by using the age structure of the standard population, indirect standardization compares 2 populations by using the age-specific mortality rates of the standard population and leaving the age structure as it actually is. The concept of age adjustment relates directly to the concept of confounding. In your analysis from epidemiology, you corrected for or adjusted for age when you stratified for age as a confounder and got a single adjusted odds ratio. While the process is different, the concept is the same in that the final result is a weighted average that gives a result that neutralizes or corrects for or takes away the issue of age. The final part of this lecture relates directly to the worksheet and your results from the epidemiology class. In the book, the discussion is about logarithmic transformation, which is used to normalize the data or provide symmetry to results that are not symmetrical. One example of a result that is not symmetrical that can be made symmetrical through transformation is the odds ratio. Logarithmic transformation provides symmetry. The worksheet assignment for this week is based on the logarithmic transformation of the odds ratio, and this graphic can help to explain how the natural logarithmic function provides symmetry. In this example, the natural logarithm of 2 is equal and opposite to the natural logarithm of 1/2. While the value of 2 and 1/2 are not symmetrical mathematically, the natural logarithmic transformation of these two values gives the number 0.6931 and negative 0.6931, which are perfectly symmetrical. From the perspective of interpretation, 2 and 1/2 as an odds ratio should be equal and opposite, and the natural logarithmic transformation provides this symmetry. For that reason, in getting an appropriate confidence interval, it is necessary to transform the odds ratio using the natural logarithmic function. This is the aim of the worksheet for you to go through this exercise using one of the odds ratios you already calculated from the epidemiology class. Take the odds ratio you have from your results in epidemiology and use your calculator to identify and get the natural logarithm of that odds ratio. Before doing that, check the values for 2 and 3 against this chart to be sure that you are entering it correctly. The next step for getting a confidence interval is calculating the standard error. This is a simple formula in the worksheet. The standard error is based on the 4 values from your 2x2 table and your odds ratio. So you can take the inverse of those 4 numbers, A, B, C, and D, and then add up all of those 4 values, the inverse of those values, and then take that number and get a square root. This is the standard error of the natural logarithmic function of your odds ratio. Then multiply that standard error by 1.96 so that you can get the range above and below your natural logarithmic function of the odds ratio, and that will give you the upper and lower boundaries of the 95% confidence interval. The logarithmic transformation involves a back transformation once you've finished getting the upper and the lower bounds. So this slide walks through the steps in theory, and this will be followed up with an example after this. But start by taking the natural logarithm of the odds ratio and use that to get the lower bound of the confidence interval and the upper bound of the confidence interval, and then you back transform to get the odds ratio again. I'm going to walk you through this with a specific example using numbers. So here I'm giving you the example from the worksheet. First, calculating the standard error for the natural logarithms of the odds ratio. So in order to get that standard error, that's the standard error you need for your confidence interval, you're taking the square root of the inverse of A, B, C, and D. So in this case, I had a 2x2 table with the numbers 221, 128, 701, and 551. Take the inverse of all 4 values, add those up, and take the square root. That gives you the standard error of the natural logarithm of your odds ratio. In this case, it's 0.124815. And to get the upper and lower bounds of your confidence interval, you have to take the natural logarithm of the odds ratio. In this case, the odds ratio is 1.36. So the natural logarithm of the odds ratio is 0.307. And then I'm subtracting that 1.96 times 0.124815. So that gives me 0.307 minus 0.2446. That's my lower bound of my confidence interval. That's the natural logarithmic function of my lower bound. And then to get the upper bound, I take the same number, the 0.2446, and I add it to the 0.307, the natural logarithms of my odds ratio. And that gives me the 0.5516, which is the natural logarithmic function of the upper bound of my confidence interval. So these values in this process will give the upper and lower bounds of the confidence interval for the odds ratio. So it's still in natural logarithmic form. So here we have the back transformation process, and so the natural logarithm of my odds ratio is 0.307. So when I transform it back, I get back my 1.36. That was the odds ratio I started with. And then I also have to back transform the lower and the upper bounds. And that will give me the 1.06 and the 1.74. In order for this to work, you'll have to find the e to the x function on your calculator and plug the numbers in as your x values to get your odds ratios back. The final step, if you're not sure if you did it right, so the first thing is go through the example to replicate that, then put in your results from your 2x2 table, and then double check the SPSS output of the results for your odds ratio and confidence intervals to check the information that was given in that output. So as a final step, check over each of the values you have and compare them to the SPSS output when you ran your analysis for the odds ratio and confidence interval, so you can see where the logarithmic transformation was included in the output. Ultimately, the process you've just done by hand is also done by SPSS. This result is identical to running a logistic regression. And this is under a function in SPSS called regression binary logistic. Now you haven't done that yet. We will make use of the logistic regression function later in the semester, but this exercise is intended to show you that you get the same result and to help you to interpret the beta coefficients that you get from that result, which essentially is the same as the logarithmic transformation of the odds ratio that you've just done. Thank you, and I will continue now to voice over PowerPoint for Chapter 2.